Alrighty, so today we're going to have a look at friction because yesterday, if you didn't get one of these, you need to get one of these. No, well, no, some people here kind of early. So. Mike, did you get one? No? Let's do that. Alrighty. Okay, so what we're going to look at today is, because yesterday we looked at inclined planes, the day before that we just sort of did net force problems, right? Sort of flat surface dynamic kind of force problems. Yesterday we looked at frictionless inclined planes. Today we're going to look at friction itself, generally on a flat surface. We'll move into ramps with friction. I think what I'll do, because I'm going to be away for Thursday with basketball, I think I might start the frictional coefficient lab tomorrow, and then that'll give you some time to finish that up on Friday when I'm away if need be. So Thursday, I meant, yeah, right. You're right. No school for you guys Friday, right? Okay, so let's jump right in here. Now you have a booklet. Basically what I did was I took this 2 or 3 page reading on friction and condensed it down into some notes. Okay, so if you want to write the notes, be my guest. If you want to wait and print them out later, be my guest. If you want to just say, they're in here, I'm good, also okay. You do what you need to do. Oh, I took notes. I took the important parts out of here. You do what you want. I'm going to talk about friction. You do what you want to learn about friction. And as I said, don't let it rub you the wrong way. Okay, so what is friction? If you had to define friction, you might say that it is a force that resists motion, and it involves objects that are in contact with each other. There has to be contact between the two objects for there to be friction, right? If you're sliding a heavy box across the floor, there has to be contact. A light box across the floor, there has to be contact. Any box, right. If you throw a football through the air, is there friction? There's air resistance, right? There's contact between the football itself and the air molecules, right? So there has to be motion. Does there have to be motion for there to be friction? As I stand here and push on the filing cabinet, lightly. Is there friction?
Yes.
Yes, there is, right? Is there motion? No. But there has to be at least an intent of motion. There was...
Just like a book seen on table, there's no friction?
Is there friction there? Is there a force trying to move it? Up and down, right? But not... I mean, the only reason that it's not falling through is because of the numbers, right? There wouldn't be any friction down, I don't think. Right? Yeah. It's kind of hard to describe, really, isn't it, sometimes?
As long as the force not up and down.
Yeah, trying to move it, right? Okay, so some cause of friction. Now, I've done a little bit of reading on friction. It turns out that there's some controversy about friction. There's still some uncertainties about friction. They're not really sure exactly if they know everything about it. Okay? So first of all, one thinking is that the object actually deforms the surface and vice versa. So if you've got like kind of like your book on the table, actually, if here's the book, ooh, that's nice and thick, isn't it? That it actually sort of makes a hole in the table. Seems kind of ridiculous, right? But sort of like on a microscopic kind of level, kind of thing. That there's actually a uphill battle that you're fighting as you're sliding it across the flat surface, right? So like a plowing force is required to move the object over these deformations, up the hill kind of thing. That's one theory.
So maybe like when like the old people say like I walked uphill to school both ways, they're just really smart.
I actually, in high school, I literally walked uphill both ways.
I'm sitting uphill.
I also walked uphill away, like going home, right? I lived here, right? You walk like this, and then there was a big valley, and then here was the school. So I walked uphill on the way to school, and then on the way back, I walked uphill both ways. Downhill, too. And then there was the time Then there was the time that two of my classmates, I'll call them, not the most academic of students, decided that it might be fun. They had their bikes. They had a 2x4. They had some rope. They decided it might be fun to strap their bikes together with a 2x4 between them with rope and drive down this big steep hill on their bikes.
Sounds really smart. Like side by side? Or
Yeah, no, side by side.
Okay.
About 4 feet apart, right, with this 2x4 in between them, down the hill.
Please let there be more to this joke.
Well, it was kind of, as a 15-year-old kid,
Well,
when
that
you
actually
see,
happened?
yeah, I actually saw it happen.
Oh, I thought you were just, I thought that was like beginning to
No, man, this is like part of my childhood.
Why? What's the point of that?
That was something that those guys just enjoyed doing. Basically, they were like, well, the MTV show Jackass. Like I think they were sort of had that idea way 20 years ahead of time.
That wasn't really
Yeah,
the original Jackass.
they were sort of yeah. I don't know. They were an amusing pair. The one guy decided he found a suitcase once, and so he tied it to the back of his bike and drove around town with it for like 2 weeks, with a suitcase dragging behind his bike, just to beat it up for like 2 weeks.
Yo.
Hey, where are they now?
I don't know. The one guy he was the guy that ran for student council president, as a joke, and won. That kind of guy. You know what I'm talking about, right?
Like Corsair?
I'm not going to mention any names, but it happens from time to time. People run as student council president as a joke, and then they win. Not Dauphin. This is like, not Dauphin. There's no big hill like that, Dauphin. All right. So the other theory about friction is that irregularities. They actually think that the book itself, the bottom of the book, is actually kind of rough like this, right? And so is the tabletop, right? And so they sort of, rub into each other and sort of lock together, that kind of thing.
Like balancing.
Yeah. This particular theory here makes sense when you think about when you smooth something, right? When you smooth it down, maybe with sandpaper or something, that there's actually less friction. Actually, if there's a point where if you smooth it so much, the objects, because microscopically they're so smooth, they're actually closer together and they're actually molecularly attracted to each other, and friction actually increases. So there's a point where you've smoothed it too much, kind of thing. You've created a vacuum almost, kind of thing, underneath a suction kind of thing. Okay, starting friction is the maximum frictional force between stationary objects. Friction is always at its maximum at the start when you try to move something. Okay, that's starting friction. The other one is simply called sliding friction. It's the frictional force between objects that are sliding with respect to each other. Now, rolling friction is actually quite complex. It's actually a subset of starting friction, because when a wheel rolls, it doesn't slide, and so what's happening is the next part of the wheel is actually at rest, and then it's the frictions between the wheel and the axle, right? There's very little rolling friction between the ground and the surface. Obviously there's some, but it's actually a subset of starting friction. It's quite complicated. We're basically going to ignore it. Okay? So anytime that we're talking about friction, we're going to assume that we're talking about sliding friction.
Even if it's a ball.
Even if it's a ball.
And it says not sliding friction, rolling friction.
No, it'll just say, we'll just sort of call it friction and look the other way. Some properties of friction. First of all, friction acts parallel to the surfaces that are in contact and in the direction opposite to the motion of the object or the net force tending to produce such motion. The long and the short of it is, friction is parallel and it's always opposite to the motion. If there is no motion, it's opposite to the would-be motion if there were no friction, right? It's always opposite to motion, right? So if the box wants to move in this direction for whatever reason, maybe gravity, maybe someone's pushing it, maybe someone's pulling it, friction is opposite. Okay, second property is that friction depends on the nature of the materials in contact and how smooth they are. Obviously, if they're smooth, there's less friction, right? There's actually a frictional number, a value that says how much friction there is between various surfaces. And it's not like, you can't say how much friction does, say, a rubber tire have. It depends. Is it a rubber tire on a wet road, on a dry road, on asphalt, on concrete, on an icy road, on glass, on steel? There has to be there has to be two surfaces for there to be this frictional number. Okay, so it depends on the nature, how smooth they are, how soft they are, and the smoothness of their surfaces. There's more friction between winter tires in the cold than there is normal all-season tires because of the rubber compounds. Sliding friction is always less than or equal to starting friction. I think we sort of mentioned that already, right? The starting friction is always more. Friction is practically independent of the area of contact. Quite a bit of controversy here. Most people would disagree with that, but there have been studies that have shown that there really is no difference, and I usually describe this with like a textbook or something. Oh, here's one. Okay. So if I've got my textbook sitting flat on the table, right, the amount of friction there as I push it across the table is the same as if it was sitting on its spine upright like that and going, right? Why would it be the same?
Mass.
Same mass, same surface. Luke has a question. If the spine was smoother, exactly. As long as the flat back of the book is the same general material as the spine, the mass of the object doesn't change, right? So the whole idea of like skinny bike tires, less friction, no, not true.
But it's wind resistant.
It is, yeah. Yeah, there is some wind resistance, right? There's also a pressure difference too, right? There's the pressure of the tire itself that matters, and so it's actually quite a complex kind of thought. But this independent area thing, again, I'll just draw the picture, right? If you draw a book like that, or draw a book on edge, right, on spine, same amount of friction. It's practically independent.
So that's what you're going to be doing?
Yeah, more or less, yeah. You assume that friction is independent of area. Starting or sliding friction is also directly proportional to the force pressing the two surfaces together, which is in direct relationship to the object's mass. Right? Mass is sort of the underlying thing there. However, if there's some way for you to reduce the weight, right? Like if you're lifting up on the object as you're sliding it, generally things slide easier. There's less friction. You're reducing the amount of normal force, right? It's technically the normal force that is providing the friction or leading towards the friction. It's the normal force, which is proportional to the mass, right? So this magical friction number, I think we talked about it in grade 11, did we? Did we talk about the coefficient of friction? I think so. I always forget. Coefficient of sliding friction is the ratio of the force of the sliding friction to the normal force. And the formula, if we were to put it on the wall, would be mu equals FF over Fn. It's the Greek letter M, and it's spelled MU. And it's a U with a tail on the front. Okay? I don't know what they use in Greece, whether they use the letter mu or they use the letter M, I don't know. When I was there, I kept wanting to, talk to some teenager and ask them what they used in physics class in high school, but my wife wouldn't let me. She thought it was weird. Do you use alpha, beta, all those things? Theta, do they use theta in geometry class? I don't know. I'd like to know this.
Yeah, why wouldn't they?
Why?
It came from them.
Well, yeah, but what do they, how do they distinguish it between F? Like, they would have to use the Greek F, which would be phi. So would they say mu equals phi? I don't know the Greek, well, it would be phi, and Fn, I don't know what the Greek N is. Find that out for me, Liam, would you? Okay, so the coefficient of sliding friction is the ratio of the force of sliding friction to the normal force. Remember from grade 11 that these are both forces which are measured in newtons, and because of dimensional analysis, those n's will cancel. And what's the unit for mu? Nothing. There is no unit for mu. It is a ratio of forces. It is just a number. It's like pi. Just a number. Okay, here's an example. I think you have the example typed for you, do you not? At one of those pages in the booklet? I think it's the same one. Am I correct? Just to save a little time.
Yeah.
It's right there? Okay, so you've got the question right there. Oh, the only thing you don't have is the picture. Go ahead and draw the picture, I guess. Mike's question was, is the normal force always opposite the weight force? Is that true? Is the normal force always opposite the weight force? I've given you a situation yesterday where it's not true. If it's on a ramp, which way is the weight force? Still down, but the normal force is always perpendicular to the surface, right?
But in this situation.
In this situation, when it's a flat one, it's opposite, correct. Okay? So what we've got here is we've got a box. I've simplified it a bit. It's a box weighing 450 newtons. It's being pulled along a level floor at a constant speed. Constant speed means something. By a rope that makes an angle of 30 degrees if the floor is shown. If the force of the rope is 260 newtons, what is the horizontal component? What is the normal force? And what is the coefficient of sliding friction? Do I have it here, or do I have to write it? No? There it is. Excellent. Okay. So, the horizontal component is Fa cos theta. In this case, 260 cos 30, or 225. Fh, did I say that? The horizontal component is Fh, and it's 260 times the cosine of 30. So 225 newtons actually goes into doing what? Yeah, right? It's like this, and then 225 is actually pulling it sideways, right?
And you have to add the one that's going up and take away from friction force.
We're going to get there. Ben is asking about the normal force. Now the normal force Fn is the difference between the downward force of the block's weight. What did I say? Oh, did I really say that?
Yeah.
Oh.
Oh, no, it's my gnarly.
I apologize, Alex. Wow, that's... I'll just blame it on the concussion. How's that?
That's terrible.
Really? I apologize. The normal force is the difference between the downward force of the block's weight and the vertical component of the force of the rope. He's absolutely right. Ben was right. Alex is right. He was right too when he asked the same question, I'm sure. Right? Yes, the normal force right here is less. Why is it less? Because this vertical component does what? Take some of the load off. Exactly, right? So the sum of these two arrows here should equal the weight force, right? The more you lift up, the less normal force, the less the table has to do the job, and therefore the less friction. So the normal force Fn is the difference between the downward force of the block's weight and the vertical component of the force of the rope. Oh, I forgot about this. I think I got these animated in the wrong order. Since it's moving at a constant speed, Ff is equal to Fh because, right, this Fh here, this friction, the Fh and the Ff are the same. How do I know they're the same? Constant speed, right? They're balanced. Net force is 0, acceleration is 0. So that means that the friction force is also this 225. What if it's not moving at a constant speed? What are you going to have to do? You're going to have to find Ff using F net equals applied force minus friction force and work it out like that. I'll show you one like that in a bit. Okay, so what is this normal force then? Well, it's going to be the weight force, 450, and I subtract this vertical component, 260 sine 30. This is my, I always get to here and I always say to myself, I've got to fix this slide. I always have to subtract the vertical component. And the vertical component is going to be 260 sine 30, or 320. It's FV. Oh yeah, this actually belongs to part B. Yeah. Yeah, this slide needs a little bit of work. So what is the frictional coefficient then? Mu equals Ff over Fn. So in this case here, it's going to be 225 divided by 320. The mu value is 0.703. Now Sean was sort of asking about why it's always less than 1. Right? Why is it always less than 1?
Because if it was over one,
Like if it was over 1, what would that mean?
it couldn't. But I don't-
Well, it would mean that what would be bigger, the frictional force or the normal force?
No. The friction.
The top, for it to be bigger than 1, the top has to be bigger than the bottom, which means the friction force has to be a whole lot more than the normal force, right? Most objects, right, like heavy objects, right, have a lot of friction, right? But that friction doesn't compare to the amount of weight, right? I mean, there might be some that are greater than 1. Like if you took, let's say, I don't know, a concrete block on,
Tie it to a squirrel.
well, I was thinking a gravel road, right?
Oh, wait.
Or concrete on asphalt. How much friction would there be?
What?
Quite a bit, right? But would it be more force than the actual weight of the concrete block? Probably not, right? Like it's just the way it is kind of thing, right? Generally, the frictional coefficient is generally less than 1. Could it theoretically be more than 1? Absolutely.
What case?
Well, something that is, like the two surfaces are extremely rough, right? And there's a lot of friction between them. All right. Reminder that there's no units on mu because the newtons cancel out, right? Okay. Here's example number 2, and I think you have it written as well. You probably just have to draw the picture, right? This one is a little different, so I'll let you read it for a second.
Yeah.
All right. So what I've got here is I've got a wooden block. It's weighing 130 newtons. It's resting on an inclined plane as shown. The coefficient of sliding friction between the block and the plane is 0.62. I've given you that. Find the angle of the inclined plane at which the block will slide down the plane at a constant speed once it's started moving. So a couple things here. What I'm saying is as the angle increases, right, eventually the block's going to do what? Slide down the plane. Okay. If I go a crazy angle, then the block's going to not only slide down at a constant speed, it's going to actually accelerate. So what I'm looking for is that magical angle that just slides down at a constant speed. But I have to get it moving first, right? Because starting friction is always more than sliding friction. So there's some angle that I can just give it a little push, and then it will continue moving at a constant speed down the ramp. What angle is that? Now it seems kind of complicated, doesn't it? Okay. Well, let's do some logic here. The point at which the block begins to slide, let's ignore the fact that we have to give it a push. Basically, we know we're going to push it. Once it's pushing, then we're just talking about sliding friction. So the point at which the block begins to slide is when the force along the incline Fd is balanced out by the force of friction, right? Constant speed. Do I have a picture here? It feels like I probably have a picture, but I don't want to click ahead. Yeah, I do.
So the FD is actually like the little bottom triangle underneath the block. Just like that.
Yeah, exactly. It's like this, right? This is Fd.
And you just move that.
This is F perpendicular. This is weight force, and you're right. All that happens is that line, that edge just slides up to there, right? So Fd down the plane, when that's equal to the friction force, then the block will do what? Move at a constant speed. Now we're going to actually do some trigonometry here. In this diagram here, maybe I'll just redraw it here. Did you say great? You didn't pronounce it very well. What you should have said was great. In this triangle here, this angle here, remember that theta there is the same as what? That angle there, right? So let's look at this triangle here. What do we know? Could you say, I wanted that to stay, could you say that if this is theta and this is Fd, could you say that tan of theta, opposite over adjacent, tan of theta is Fd over Fn, right? But Fd and Ff are the same, right? Fd and Ff are the same, right? So by looking here, I've got tan theta is FD over Fn, but because FD and FF are the same, tan theta is FF over Fn. Well, what other magical thing did we just learn about that is also equal to FF over Fn? Mu. It is kind of crazy. So the tan of theta is equal to the mu value, so that means theta is simply the inverse tan of the mu value, or 31.8. It seemed a lot more complex than it really needed to be, right? It's actually quite simple when you stop and apply some logic to it. Well, the only real logic that you have to come up with is this FD equals FF and recognizing this tan theta. Will I expect you to be able to do that? No, it's just something that sort of we're pointing out to you. Kind of thing. Okay? I will likely have to do some more problems over the next few days.
How would we like see that?
You wouldn't. That's why I'm pointing it out to you. I wouldn't expect you to come up with that on your own. Okay? Okay, the rest of the booklet, there are friction questions. There are 10 of them. They are sort of like thinking kind of questions. You should probably do them. At the very least, you should probably read the question and come up with an answer in your head. Do I know how to answer that question? There are some problems, 1 to 11. There's a QR code there with solutions. There are answers provided both for the questions and the problems themselves there. I'm going to give you the remaining 25 minutes or so to work on those, work on some stuff from yesterday. I've got to figure out how I'm going to handle the next couple days. Yeah. I don't have a plan yet, so we'll work on that. All right, that is all for today. Oh, I guess I should have given you this here. In other words, the block will slide at a constant speed when the angle of the incline is 31.8. No matter what the block weighs. Did you notice that? That we didn't use the mass at all? Right? It doesn't matter how heavy the thing is. 31.8, it'll slide. If it's greater than 31.8, it will accelerate.